And this is a grade 11 physics question about standing waves. It's question 33 from your workbook, the most kind of mathematically intensive question that we get, so we'll do that one out so you have an example to study from for tests and exams. Standing wave pattern in a string is observed to have 5 antinodes. There's a node at the beginning and the end of the pattern. The distance between the first and fifth node is 33.6 centimeters. The speed of the waves is 7,756 centimeters per second. What frequency must the string be vibrated at to observe 2 antinodes? So we're starting with the image here on the left, where there's 5 antinodes, and we want to, within the same length of string, vibrate it at a very specific frequency so we see the pattern of 2 antinodes. So before we get into all the math, the strategy I'm going to employ here is to figure out the frequency to see 5 antinodes, take that frequency, divide it by 5, that tells me the frequency to see the natural frequency, or 1 antinode, and then I double that, or multiply it by 2, to get my answer. Working with what's given here, I'll just write down the velocity. So I have it 7,756 centimeters per second. The distance between the first and fifth nodes, and now be careful, the nodes start numbering from the start 1, 2, 3, 4, 5, 6. There's 6 nodes, 5 antinodes, so you do not have the full length of the string. You have only kind of 4/5 of the length of the string. It's 33.6 centimeters. So with that information, you're given a set number of waves contained within a distance. You can figure out the actual wavelength. So 33.6 centimeters contains 2 full waves. So I'll trace that out here in blue. Starting from 1, there's half a wave, 1 full wave, 1.5, and then 2 full waves. Okay, so 1 crest and 1 trough form 1 wave. So dividing both sides by 2 gives you the wavelength, 16.8 centimeters. You can leave your answer in centimeters because the velocity is given in centimeters per second, so you don't have to worry about changing anything to meters for this one. So we have wavelength, we have velocity. With that information, I'm going to figure out the frequency to observe 5 antinodes. So wave speed equals frequency to observe 5 antinodes times the wavelength. Speed is 7,756 equals f5. Again, the 5, it doesn't mean anything more than there's 5 antinodes in the full pattern. Wavelength is 16.8. Divide both sides. 7,756 divided by 16.8 gives you 462 hertz. Is the frequency to see 5 antinodes. So in the diagram on the left, there's 462 waves passing by a certain point every single second. That value is 5 times the natural frequency, which is the frequency to see just 1 antinode. So that's what I'm going to kind of work towards. So F5 equals 5 times the frequency to see 1. Well, the frequency to see 1, the frequency to observe 2 is twice the frequency to observe 1. So using that, we're going to figure out the frequency to see just 2 antinodes. So I'm going to just kind of erase that and start over here. So first thing I'm going to do is step by step. Frequency to see 1 equals F5 over 5. So that's 462 over 5 hertz. So the frequency to observe 1 antinode is 92.3. To double that, so the frequency to see 2 equals 2f1. So that's 2 times 92.3. So the frequency to observe a pattern with 2 antinodes is 185. It rounds to about 185 hertz. Again, the frequency work at the end is probably a little more confusing than it has to be. Please go through it very carefully. You find the wavelength. Okay, so you find the wavelength, and then using speed and wavelength formula, You figure out the frequency, and then once you find the frequency to C5 antinodes, work backwards to get the frequency to C1, and then work backwards, or I should say work forwards, so you double that to get the frequency to C2.